Hi everyone. This is going to be a fairly quick whistle-stop tour. There's a lot to cover, but I'll try my best to cover as many things as I possibly can. About my sort of research project that I've been working on for the last few months, which has been attempting to automate some aspects of analytics. So just to sort of prepare the ground, a just very quick definition of what I mean by automated analytics. And it's easier to understand if we think about it in reference of sort of the standard data ingestion pipeline for app companies and websites and game developers. You have a client who's doing some things with your product, and then there are things that you're interested in that person doing, so you're going to capture events when they do something that you want to track. And that's going to end up in a database through some convoluted process. And then you employ analysts or game analysts or data scientists, and they're going to take stuff out of that database and they're going to produce reports or something useful. And so that's the bit that I'm interested in this particular pipeline. We've got event data in some database somewhere, and we want to do some analysis without someone having to get too involved anyway. So to sort of frame the problem a little bit closer as well, I'm not talking about automated data science. I think that's far too unreasonable, and as Xiaozi, is that all right? Okay, sort of highlighted, there are lots of pitfalls. The area I was more interested in is thinking about an analyst and helping them to maybe get a little bit closer to the interesting parts of their data sooner rather than later, especially when you've got very fast iteration times over products. You want to get to the good stuff as soon as possible, and if an automated tool can help you with that, then I think that's a good thing. So I'm going to jump straight into a demo of sort of the thing kind of working, and it'll probably make it easier to understand what's going on. So this is Tom's automated analytics system, which I call Taz. You can't really see the icon, but there is a little Tasmanian devil up in the corner. You'll see him later on. But so there's a few features that I've built so far. The first one is funnel analysis. The second one is kind of a temporal analysis around churn points, and the last one is spend. So basically the two main areas that Xiaozi was talking about. So the idea with funnel analysis is, I'm sure everyone knows about funnel analysis, but very, very briefly, the idea is that you have some milestones that are important for your product, and you want us to understand how many users you've lost up to that milestone. And then you're hoping that if you can get enough detail of that sort of funnel analysis, that you can pinpoint some places where there's problems with your product. And so the system that I've been working on in this particular game case, this is from live game data, which I'm going to call Prison Break, although I've had to anonymize everything. This is a sample of 10,000 users from the game from a particular build on a particular period of time. And so in this case, the system has made a funnel of 3 parts. And from the first to the second part, you can kind of see there, they've lost 50% of their users, and then another 16% from the next part. Now, that's not particularly useful at the moment because you have absolutely no idea how it's sort of segmented the data up to produce the funnel. So the next thing the system tells you is or it tries to characterize what makes that component different from the other parts of the funnel. And at a very high level, I'll go into some more detail later on, but the way this does this is the system is effectively looking for differences in the behavior of the underlying structure of the product. And you're hoping that the structure in the event system is a good proxy for the structure in the app. And that if there are different patterns with which the events are firing, then that kind of corresponds to some difference in the actual behavior of the product itself. So, and to sort of try and explain what the system's doing here, it basically lists out what events fire for the first time and in a particular stage of the funnel, and never fire for the first stage for the first time in another stage of the funnel. So in this case here, the first stage of the funnel is characterized by the first firing of the tutorial events for this game. So if you're a games analyst, you can be like, oh, okay, so by the time I've done the first tutorial, I've lost 50% of my users, or around that kind of time. And then the next stage of the funnel, you can see these other events here. So the game has like this multiplayer aspect, which is like about clans. You do the first tutorial, and it's like, hey, join a clan. And so that makes sense that this is the first firing of these sort of clan events. And also you can see there's like a market purchase event and a season event, which is, so basically the game is kind of played in seasons. I won't go into too much detail about the game, but it's not necessary for the moment. But yeah, the game is playing in seasons and it's identified that. So now as an analyst, you can be like, okay, first tutorial is the first stage of the funnel. Encouraging them to join a clan is the second stage and also the new season. Now, most analysts have the tools and the capabilities to do something like that as it stands, but something that most analysts perhaps, or the sort of the dashboarding services at the moment don't offer is sort of a predictive aspect. Now, this is an interesting topic because we've just been talking about the pitfalls of prediction, but what I've tried to do with this sort of application is instead understand some signals in the actual data rather than make a black box predictive model. And it's not going to be perfect, but to try and help with that, the system automatically removes all data that correlates with time. So you do have, you understand that there's something at least slightly causal in this. And I'm not saying that this is like the model that's going to tell you everything about your product, but if you're an analyst, maybe you can take each of these points and go do a bit of a deeper dive and then go and produce some better analysis. So again, I'll go into a bit more technical detail later on, but the way the system does this is because underlying the thing that makes all of this possible is the system produces a model of the underlying event data, which is how we did the funnel analysis. But from that model, it actually becomes relatively easy to aggregate over a user's data. Because you have this you have all this metadata about the actual underlying structure, you can collect aggregates. And when you collect aggregates, you can then do some sort of NLG on the names of the aggregates, and then you can build a predictive model. So basically, that's the thing that makes this a bit unique, I suppose, is that we're taking the event data and aggregating it without any human intervention. So just as I'll pick out a couple. So the highest level of the decision, this is a decision tree, by the way. I tried some other sort of rule-like systems, but they still didn't outperform a decision tree in terms of understanding, so that's why I went with that. But here you can see that basically the days played ratio is at the top of the tree, and that if your days played ratio is less than 85%, you go down this route. Here's one which I find quite interesting, that is saying here that if your loot time, so the way the game works is that there are 4 slots for your loot, and you then unlock that loot later on, like maybe a day later. Bearing in mind I've removed everything that sort of correlated with time, like less than some very small value, the fact that if the users get the second loot box it's quite predictive of a big difference in the churn of the users. That tells you there might be something about the difficulty, or at least there's something worth exploring about getting that second loot box that is at least interesting. Another interesting one I found was the load times between these two events. So this is basically saying if the time between this event and the previous one is less than 93 milliseconds, then you churn with you're twice as likely to churn. Now that might be because it's a correlation between the previous event being one particular choice the user has made, or maybe it is actually load timed. But the idea being, as I've mentioned, you can go and look into it. So that funnel system so far, it's kind of looking at the product on a high level, saying like, what's the behavior of the app, and how does it change over time, and can we understand how the user's journey, how users churn based on the behavior of the app. I also thought it would be interesting to do a kind of a user-based analysis as well. So when the churn hotspots part of this, please load, okay. Churn hotspots is about doing a temporal analysis of the user's behavior around the time that they churn. So this is, my definition of churn is that you never come back for the purposes of this, right? But you could tweak that. There's plenty of other decent definitions of churn. But the idea here is to look at the events that fire around the user churning, and then maybe we can understand something better about our app. So the first thing that you want to probably understand is the events that actually fire, or by percentages. So these first 4 events here are felon escaped, push notification, which absolutely makes sense, UI change, which isn't particularly helpful because the UI change is going to change a lot, but there's actually something we can do to make that information more useful later on, and then felon death, and that's another in-game event. So of the top 4, we've got 2 which are sort of game-based events, and then 1 which is kind of about the UI, and 1 which makes complete sense. But still maybe you can be like, okay, well, it seems that users are churning after a game. It's not like when they're stuck on some UI element or something like that. Or maybe it is because it's the UI change thing. But you know that there's something about the game that's turning people off. But you don't have any information at the moment about how many games they've played, because it might be that they've churned after 20 of these events have fired, or it might be that they've churned after 1. And so the system goes and sort of spits that out, just median number of times the event has fired for users who churn with that in their window. And if we sort of highlight the felon escaped and felon death events, we see there are 4 have fired. Now, from knowing this game, I know that basically 4 events are going to fire per game of those different events. So you can sort of reverse engineer that and say, well, people are churning after they played 1 game, which makes sense. People are going to try a product and they're going to decide pretty quickly if they don't like it or not. But at least you have a point, a frame of reference to be like, well, we have to optimize that first game closer instead of spending more time on our UI or something like that. Now, this is probably helpful to some analysts on some level, but as I mentioned before, that UI change event being one of the last events wasn't helpful at all, because you need to know more, you need to know finer grained information. So what the system does is it looks at the categorical data which is sent as the parameter with that event, and then it will do basically a non-parametric test to see if I split the churn rates by that particular parameter, are there statistically significant differences based on that test? If there are, go and spit it out because it might be useful. Again, this is no guarantee of anything sort of amazing or enlightening, but visually you can see that there are clearly big differences between where users churn in terms of the UI location parameter. And we can see here that the 2 biggest peaks are Enter Prison, which is kind of like a loading screen, and then probably more interestingly at the police locker. And the police locker is where you load out your gadgets and your weapons. And we've seen that users churned after a game, but that particular UI event is going to fire before a game. So that probably tells you that there's something causal about the fact that they're seeing the screen and churning. And from having some experience with the game, the UI of that part is terrible. So I'm not surprised that people are churning around then, but at least you can go and say, right, we need to work on the police locker and maybe design a good test to work on a better UI for it. Same thing down here. So it split the tutorial event by the UI name, and you can see that there are some fairly big differences between where users churned based on the UI name for the tutorial event parameter. But if we just sort of highlight the 2 biggest peaks here, they're on what's called felon cover and felon health, and it's a tutorial based on finding cover in the game and. Oh no, it's felon adrenaline and felon cover. Yeah, that's right. And adrenaline and the cover tutorials are very, very important because they're key game mechanics. And they have the highest churn rate as a percentage amongst their users. So clearly something about those tutorials are causing people to go, there's a problem with this, I don't like it, I don't understand, and then I'm leaving. So there are those 2 features. I've also done there's a spend-like feature, which is basically looking at trying to predict if people are going to convert to a spend user or not. It's very similar to the funnel funnel analysis, where you have aggregates, you try and predict something using a decision tree. But that's basically what I've been working on. So I was a bit short of time doing this presentation, and I did have a bit about what I tried which didn't work. I put these slides online, and there's sort of a little appendix about all of the different things I tried. I tried a lot of neural network-based stuff using like variational autoencoders, recurrent neural networks, basically the kind of like deep autoencoder, t-SNE kind of stuff to do user segmentation, and it was just too unreliable. So if you want a bit more information about that, it's in the appendix. But to go straight to how it currently works, the key difference between those things I tried before and what I've got working now is this idea of how can we actually pass some metadata about the structure of the product. So under the hood, there is a structured interpretable model of the event data that the system produces automatically. And I do a lot of analysis over that structure to help me try and figure out the funnel, et cetera, do the aggregation. And so that's the key thing. Other things which I think are important as well are doing statistical analysis of event firing patterns and parameters. So no deep learning, anything like that, no black box techniques. The automated aggregation obviously makes it possible to then go and run anything I would want to try over the user's data. And then kind of in line with all of this sort of stuff, I sort of constrained myself to only using interpretable models, because then I can sort of, having done some analysis of this product already, I can already say, okay, well that seems to align with what I already know about this or what I believe about this, and so maybe there's something to it. So that model that I keep on talking about of the sort of underlying event structure is generated by a process mining algorithm. Now, I'd just be really interested to see a show of hands. Who's heard of process mining? Good, that's better than I thought. I have to thank Nima for putting me onto process mining, because I'd never heard about it before either. But I think it's super exciting as a branch of sort of mathematics, because it's all research based on analysing event data and understanding the transitions between events. So its main output is basically a graphical representation of events and the transitions between them. For some reason, all of the researchers of process mining researchers are Dutch. I have absolutely no idea why, but that's the place to go. So here's an example of a very trivial sort of process model using a package called Prom. I'll talk a little bit about Prom later on. This was a sort of a prototype I did for a monkey simulator. So the idea is that I had a monkey with a state that I couldn't see, it wasn't revealed to me. All I could observe was the behavior of the monkey in this sort of simulation, and then I was trying to infer statistically some interesting information about the monkey. So the monkey starts here, and then he has 3 choices. He can play a game where he earns nuts, he can take a nap if he's tired, or he can just leave the experiment. When he's played a game, so that would correspond to him moving from the start point to the play game event, he can play more than one game. Another weakness of, well, not another, but a weakness of process models is that it provides no information about how many times an event can occur in sort of a loop. But it's identified the fact that the monkey can play multiple games. After he's bored of playing games or whatever, he can eat his nuts that he's won, or he can trade them in for a super great banana. So, he has the choice to do that. Again, process models won't tell you anything about why he would choose a particular choice, but it's representing that information. And then after he's had his snack, he can take a nap or he can leave. So that's the kind of stuff that process models are interested in producing. And hopefully you can see, if you guys deal with event data, how this would extend to your kind of problems. Now, this is all well and good, but from working with these things for quite a while, there are quite a lot of problems with actually using process models in the real world. And the first one, there are sort of implementation issues, and then there are theoretical issues. So the first implementation issue is that Prom is just the worst piece of software I've ever had to deal with. It's so slow. Like it will not run over 100 megabyte of data in a reasonable period of time. It will use like 48 gigabytes of RAM or whatever, and it's got an awful UI, and you can't export it, so you can't actually use it like an API and test things out if you've got some custom data source. So it's immediately like a turn-off. And also the problem is that when you go and run one of these algorithms, if it actually runs, you tend to get very bad models to start off with. You get like these spaghetti-like models where every event connects to everything else because of some very esoteric use case where some rare behavior has occurred. So you run this thing, you finally get it up and running, and then you just look at this thing and you go, I have absolutely no idea what this thing means. And kind of in line with that, the problem, there's the implementation problem in the spaghetti model side of things, because the default parameters don't tend to be too good. But on a more theoretical level, there's no like killer algorithm. There's no one process mining algorithm which just absolutely, it destroys everyone else in terms of fitness and generalization. And that's something I should probably note as well, that they just as a whole, all of the algorithms tend to produce overly generalized networks. They tend to favor that kind of behavior rather than something more concise and accurate, unless you're able to tune your parameters quite carefully. So having been faced with these problems and still wanting to use process mining, I had to think, what am I going to do? And the sort of answer I came up with was to combine a process model with some other analytical techniques to kind of enrich the model, so that we can sort of work around some of the problems with process models and get something which is more usable in the real world. So to create this kind of hybrid miner, there's a couple of things that I do. So when you've got like these spaghetti-like models, like something like a UI event is going to have lots of inputs and is going to have lots of outputs. So that's going to be one of your main sources. But there might be sort of contextual information about that event, which allows you to actually duplicate it and say, right, we're going to split this UI change event off into 4 different cases where it seems the UI is triggered here, like maybe before a game, and then you've got like the main option UI or something like that. And you can actually do some analysis over that context and also the parameters to actually split those cases up, and that helps to produce less spaghetti-like models. And then something I've mentioned before as well is this idea of like repeat events, that process models will tell you nothing about how likely an event is to repeat. The system actually incorporates some temporal analysis around the times between events in a loop, for example. So you can basically do clustering over the times and say, oh, okay, well, it appears that if you're saying like 6 have occurred, but 3 of them are very close together temporally, and then another 3 are very close, then it's likely that there are actually 2 instances of 3 events or something like that. And you can also do some, it also does some kind of smarter stuff as well, where it actually looks to, at the parameters of the repeat events to look for patterns in the position. So say, for example, one parameter value only occurs on the first event in the sequence, then you know that there's some indication that you're actually at the first and maybe not the sixth or something like that. And the last thing the system does as well is it uses log segmentation. So we're all familiar with the idea of doing segmentation over sort of a feature vector, but you can actually do segmentation over traces. And my personal preference algorithm for that is something called ActorTrack, which basically adds a new trace. A trace is like a user's data, by the way. It adds a new trace to a model if the fitness doesn't go below a particular threshold. So with all of these components in place, we can now do aggregation, and we can understand how the aggregation system works. So first of all, I collect metadata about the process model by looking at loops, choices, iterating over choices that users can make, whether they're automated by the system, something which is just part of the implementation, or actually a choice of the user. Also looking at linear sequences of events so that we can avoid aggregating over, say, 4 events. We can concatenate those into one chunk and reduce the sort of the amount of aggregates that we collect. And then you can also aggregate over the event parameters. And that's the reason why the repeat event analysis is really important, because say you have 3 transaction events, which might be sending different data. Like the first one might be to say, okay, we're going to do a transaction. The next 2 are like to reward them with this type of currency and then another type. If you're aggregating of those 3 events separately, you're going to get garbage, because really they should be considered as a whole. So by doing this analysis of the repeat events, we can concatenate those events together and aggregate over that cluster as a whole, and then you get slightly better quality aggregates. And then not only can you aggregate over the sort of numeric data that event will send, but you can split it by the categorical data. And if you're careful, and if you remove things which correlate, which are sort of user level data, and you remove sort of categorical data which correlates with each other, so that you're not aggregating over a category which is basically a duplicate, then you actually start to get something which is kind of usable. So just as a side note, has anyone used is it Crisco's tau as a correlation measure? No? Really good measure of correlation between categorical variables. So I highly recommend everyone checks that out. Once you've got this sort of stuff, then you have a feature vector which represents your user's data. And if you're just not dumb and you actually structure the names of your aggregates, you can parse that structure and generate sort of sentences. So you can understand. So in your decision tree, you haven't got like nonsense, like just some bunch of underscores with some really abstract names. Now the way the system works at the moment. It collects about 10,000 aggregates, something like that, just on average. And most of those contain very little information. And if you, and that's probably to be expected, because it is an automated system. But when I've looked over the aggregates and thought about what's actually valuable in it, it tends to hit most of the right notes of what I would kind of do if I was hand collecting the aggregates. And I think that's the important thing. As long as it's not missing out information, I think there's probably some value to collecting all of that information. So that's the aggregation, and that's how we do the funnel prediction. To actually do the funnel analysis generation to get the different stages, I kind of mentioned this before. The idea is to analyze the event firing patterns and to segment the log into distinct periods based on which are kind of like a proxy for the underlying behavior of the data source. So we know that when we're firing a tutorial, or the user's involved in a tutorial, the events are going to look different from when they're just in the core game loop or something like that. And so the system is trying to identify that kind of behavior and then split the log up based on that. And so the way this works is, if we take the example of a tutorial again, if we were to look at the density, like a density estimation of when that event fires, so this is just like some normalized time, there's probably going to be peaks, well, maybe there's not, but in some cases there's going to be distinct peaks of when that tutorial fires. So there might be like a fairly fixed number of things the user can do before a tutorial. So you might get, you're probably going to get some, in that case you would get a big peak, which is like they're doing a tutorial. And then maybe you get, you have another tutorial later on, so there's some period of time when the tutorial event fires again and then again. Obviously the peaks decrease in size because users have churned. So the idea is to use a Gaussian mixture model to effectively model as many peaks as possible. Now, from my experience of doing this, the Gaussian mixture models just overfit like crazy. Like they just want any tiny deviation on anything slightly non-Gaussian, and they're like, yes, we need another model. But that's not too much of a problem with the current sort of formalism that I've used here, because I then basically take each component of the Gaussian mixture model and just represent it by its mean and its variance. And so if you've got like this tiny little normal distribution, it's probably just going to overlap with kind of the interval that represents another peak. So, and it's occurring at a very similar time. So it's likely that when it's going to occur in the same funnel as the other ones. So it's potentially an issue, but from my experience of running this, it seems okay. So now we run a Gaussian mixture model for every single one of our events. And then what we do is we build a graph based on if a component's interval that represents it sort of in this model overlap. So for example, I've used the same one here, so it's not particularly helpful. But you see for the spend event and the tutorial event, maybe the first time a spend occurs, I mean, it's not going to happen, but it overlaps with the tutorial. So you can imagine this graph, the first component of the tutorial and the first component of the spend, they're going to be connected. And then the weights of the edges is determined by the overlap or something like that. So now you have this graphical representation of when events occur, which is kind of like this conceptualization of the underlying behavior. And then you segment the graph just using any graph segmentation technique, and you make your cuts based on the segments. And then because they're all occurred in like some time normalized area, you know that ones which are in the same cluster are likely to represent some period of time. And so there you have your funnel. So there's a lot of other stuff that goes into this, which I don't imagine I have time. I know I've spoken extremely fast, I imagine I might even have some leftover time. I don't know, but there's some other sort of nuances and other bits in the spend and some other things that I'm working on right now, like for example, temporal analysis of spending behavior. So trying to understand the different types of reasons that a user would spend, like the motivation for it, but I don't have time. So I just wanted to make a very, very quick addendum about sort of one of the main things I learned, which is that this code base at the moment takes like a day and a half to run, which is a very long time for not very much data. So we're only talking like a gig, like 10,000 users is probably like a gig, right? So I opted to do everything in R for one reason, that I really like dplyr. Does everyone agree with me, right? Dplyr is great. Okay, so and I just think pandas is awful. But anyway, so it's clearly not optimized for time. But I started looking into like the reasons why R was so slow, and it seems like the reasons are really, really bad. It's like, so I did a test where I took the correlation, I computed a correlation matrix of like a 10,000 by 10,000 size matrix. And in R, this took something like 10 minutes. And I just wrote some C code using like a Open Blast, like it's a linear algebra library. And it took like 4 seconds. And you're like, that's time when, if I was working in a job, that I would have been sitting around doing nothing. And I don't like sitting around doing nothing. I'd rather do something. So because I'm on a public forum, I just thought I'd make this point that I think we've had enough time in the data science community, and especially in sort of data engineering, to sort of say, right, we kind of know what we're doing most of the time. Can we stop and not keep on working on Spark and MapReduce because they're terrible? And can we actually think about what we've learned and built something better, like maybe a new language or maybe something else which kind of fits our problem a little bit better instead of bashing away at this thing which doesn't work? So thank you very, very much to King for inviting me. I really enjoyed actually doing this presentation because it consolidated a lot of my ideas. Taz is kind of in a state where it can be used by someone else, and I'd really be curious to try it out to see how it breaks, because it inevitably will. So please contact me on tom@coajoint if you want to. And I just put up a website today for tazanalytics.co.uk, and maybe if anyone cares, that will be the place where it will be. So that's me. Thank you.